Hey, good afternoon, everybody. I know it's 5 p.m., so you are tired, so I will not burden you with a lot of science. Since I missed most of the workshop today, so I will talk about things I've been thinking last year, but also is mainly to invite the conversation about what is machine learning, what is the knowledge, what is the meaning of being a human. So most of the science part, which I will get to that, right? Most of the science part that I will be presenting today is based on the work that I worked with a student. So unfortunately, he has discovered the meaning of being a human and joined JP Morgan after he worked with me. So one slide about what is galaxy evolution. Small guy merge and become a bigger guy, right? So that's what we want to understand. And the question that we try to answer, of course, is the inverse question, meaning that given the limited observation that we can do for the local galaxy or the Milky Way, try to understand what happened to the galaxy. And of course, this type of question has invited us to run a lot of simulations to try to understand how galaxies form and evolve. And the classical law of how we try to understand this question is to say, if I can find some analog in my simulation, then I can say maybe I can understand how the galaxy form. But that approach, of course, is futile by definition, because what we can observe of course, quite limited, right? So given that you only know, say, the halo mass, the stellar mass, there are different routes that can lead to the same endpoint, which means that one direction is straightforward. You can run n-body simulation, but the reverse question is very hard, because it is a probabilistic question. It's one to many. And this leads to the question about what is the meaning of being human. So this is a paper from Nature in 2000s. Even back then, people have been debating that we are no longer human. We are just some meta-human doing some meta-science. And of course, what they are saying is that the simulation do know a lot more than what we know. So you have the entire table, but we are just picking crumbs from the table that try to understand bits and pieces that is already in the simulation. The question becomes, now we have machine learning, can we make to go back from meta-human to become more human, right? So this is the question about what we should ask. So what is the meaning of being knowledge? And what is the meaning for being a human? So I would argue that one simple a definition of that is to be able to ask question and answer the question. So if you think about question, quite often it comes in the form of a prompt, right? So you give a prompt and try to ask what are all the ways to satisfy the prompt. And this is from DAO-E2, because Australia and kangaroos. So generative models itself is very close to how we define as a human, because this gives us a way to answer prompts. And this is why people are so excited about what Joe is working here, because now you can ask a prompt and try to get the responses. So, of course, all of you know what is a generative model. So I want to just reiterate a little bit. So fundamentally, most of these two are just a density estimation problem, right? So you have some training data, and you try to find the best way to describe the training data. So, of course, if you can describe the distribution of the training data, then to answer the prompt is fundamentally quite easy. So if you can describe the distribution between the x and y, then you can just say given any x, I want to recover all the possible y's. Right? This, of course, is why we are excited about this thing, because of SBI. So a lot of things, even in the simplest sense, right, not the human level, just astronomer level, we often want to ask, given cosmological parameters, can I write down all the possible realization of the universe? So at this point, I love to really distinguish the terminology a little bit, because in machine learning, we love suitcase terminology, meaning that one word means everything. In astro machine learning, it's even worse. So when we say emulator, we mean literally every single thing in machine learning, right? So at least I want to discriminate between these two terms, the generative and discriminative. And this is not new term, right? So I am like teaching statistical or machine learning this semester, we often talk about what is the distinction, right? So what you try to do is to say I want to infer the posterior. Say I have some classes of observation. Based on the observation, I want to infer the class. The class can also be labels. So we have the likelihood and the posterior. And one is easier than the other, right? So if you are emulating the posterior, you are doing a discriminative like models. If I am emulating the likelihood, I am doing a generative like models. And in principle, even back in the 1980s, we know that if you can do a generative models, you should always do a generative like models. Why? This is a simple case, right? So this is saying that given a certain like classes, what is the distribution of observation? So the distribution itself contains a lot of information. But if you treat this as a discriminative models, then you're just finding the boundary between the distribution. So you're not describing the distribution, you are just finding the best way to find the best point that will best separate that. So you can go from here to here, but you cannot go back from here to here. So this is why when you can do unsupervised learning or generative models, you should do that. Just like very hard, because this guy is much more higher dimensional than this one, right? So this one, if you're thinking about the image, this is a conditional distribution of 1 million dimensions. This is a conditional distribution of 5 dimensions of your labels. So this is why people tend to subject yourself to discriminative models, but what you should really do is the generative models. And in fact, this is also not new in machine learning. You know, I'm teaching the courses about approximate inferences. This is the ultimate goal of science, right? Since the 1970s, people talk about approximate inference, variational inference, ABC. My statisticians want to do that forever, just that they fail for many like decades. And then like deep learning come along, and even that we have struggled quite a bit. So for example, like when we get like very excited with GAN do not solve the question, because GAN suffer from what we call the mode collapse, meaning that you're not describing the distribution, because for the adversarial loss, it's very hard to ensure that you capture the whole distribution. But of course, we have also heard a lot in these conferences. Things has drastically changed, right? Like normalizing flow, the diffusion like models are all very powerful too. And it's just more principle. In fact, it's also very poetic, because you are disentangling all the structure back to a Gaussian field. We know that all the structure that we see today come from a CMB, which is a Gaussian field. And now we are doing the inverse process, right? So we have talked about that. People have the gut that maybe we are there, right? So maybe the normalizing flow and diffusion model is really good enough that we can be clear that we are capturing the distribution. So this is something that my group also like worried, like, are we doing the right thing? So like Susan talked about that a little bit. Like we have been working on this for a little while. So we just try to say for a reionization field, can I describe the distances between the distribution? So this is called the fractured like distance. Like due to sampling noise, you do not expect this to be 0. Like when you do a truth cross. But GAN is really bad, right? So the GAN is because of mode collapse. You're not capturing the distribution, and diffusion and models is doing quite good. In fact, like the normalizing flow is also quite okay. So suddenly we have shown that, wow, you know, for the first time, maybe we have a way to do the generative like models for real, right? After 50 years of statistics. Cool, right? So the images, text become quite straightforward. We have ChatGPT, we have all the mid-journey seems to be capturing the distribution quite well. As Australians say, cheers. No, right, it's not quite yet. Because like the images is not what we observe in most like cases. In fact, what we observe quite often is a point cloud. And for the simplest like approximation is actually a graph. So graph is actually much more like natural than most of the observation. You can smooth out a point cloud to be a vector field, but your observation itself is fundamentally a graph or a point cloud. For example, you know, look at the merger tree. If you fix like any moment of time, quite often you do not care about individual galaxy. but you care about the relation between the galaxy. So this is, of course, a graph. But graph is also like very challenging, and this is why even in machine learning, like this is not a solved like problem. First of all, the graph has the problem of varying the dimension, right? You have 10 nodes, you can have 10 galaxies morph to become the Milky Way. You can have 20 galaxies and merge and become the Milky Way. And graph also have huge redundancy. So you have like a loss of symmetry groups. So of course, you have the rotation group, the parity groups, but also unlike the images. So if you shuffle the indexes of the images, is not the same image because the index itself means something. But for graph, you at least has a n factorial redundancy. And this is why it's extremely hard. And this is why most of the work that we have heard so far are doing sort of the discriminative like models, right? So you just say, given some molecule, I want to know the label. The label can be like omega m, can be the stellar mass, can be the core cups of things. We have heard a lot from like Christian, like these are like amazing work. But one can ask, can we do the inverse like question, right? So not doing a discriminative models, let's do the generative task, meaning that given the prompt, can I generate all the possible graph? And this is, of course, a more challenging task because of the huge redundancy that I mentioned. And this leads to a lot of new idea in the machine learning world, which is injecting strong inductive biases to be able to learn the reverse route. So you're injecting a lot of symmetry of that. And this leads to one slide that no one should care, so the technical slide. So what we do here is a combination of few things. So what make it possible to generate graph? First, you need a normalizing flow, so you can go from one end to the other. We use a neural ODE. The message passing in the neural ODE, the integrand itself is a graph. And this is important because this is the way that you can input any dimension. And this is why you can actually have generate 10 nodes. You can also generate 20 nodes all with the same function. Right, so you can deal with dimension. And this is also quite handy because you can inject all the equivariance that you want within the message passing. So I love this work a lot, right? So this is I feel like it's one of the work that I enjoy the most because it's like the avenger of methods that I like normalizing flow, neural ODE, graph network. They all put together and make this possible. So, but more plainly speaking, what we have learned is the following. So you take some cosmological simulation, you have the progenitor at high redshift, you have the result at low redshift. Essentially, you try to learn the joint distribution between them. So you are not learning given y to read out x, but you try to learn the other way around, given x, all the possible y, or a joint distribution. And why this is important, right? So I keep emphasizing that what is being a human? Being human is able to ask questions. And it's by exactly like this type of models, you can start to ask what form the Milky Way. So you can read out all the possible ways to form the Milky Way. Of course, anchoring on the knowledge of your simulation. And this is, of course, why Bing is better than Google, right? So now just finding the closest analog is not trendy. So this will not generate a knowledge. It's by answering the question that gives you the more knowledge. So if you're looking for analog in the simulation, you are doing a Google search, which is very 2022. Now you should do is Bing, right? So you try to do a search more effectively. So more specifically speaking, we learn a conditional distribution. We condition on things that we think we can observe and try to probabilistically generate all the graph that could make this galaxy. Make some connection that things that we have heard about. So for this work, we're focusing on one fixed time and look at all the progenitor. In day one from tree, it actually follow the main progenitor, right? So it's the different approach is quite complementary. You might ask, why do you not generate the whole tree? Because we are not there yet, because graph generation is quite hard. So, but what can you do with this type of very hard inverse question that you couldn't do with a discriminative network? So the first thing is to find unknown, right? So once you have captured this, as a joint distribution. You can say something is normal or something is outlier. So this is not possible if you just have the boundary between the classes. And to show you what we can do, for example, you start with a system from TNG 300. This is, of course, a normal system, has a high likelihood. And let's say you are a superpower like aliens, you push your galaxy like away. This system will look quite normal by eye, but it will actually have a very low likelihood. And this, of course, is very exciting because now means that you can find outlier system not only in the spectra or the image space by looking at outlier in the configuration space. Even individual of them looks quite normal. Putting them together looks weird. But the other thing, as I mentioned, like this is for free. If you can do the hard question, then you can do the easy question. Then you can infer the posterior. Not only you can infer the labels, you can infer the posterior of all the things that you care about, right? We heard a lot about, meaning that now if you have given X, I have all the Y's, then given Y, I can read out all the X. So here is showing that, let's say I observe some progenitor at high redshift. I can infer not only like deterministically, but a posterior of what the galaxy would become after it has emerges. So this is actually an 8-dimensional posterior. I'm showing 3 of them. This, of course, also tied to a lot of things that we have heard about. So again, if you can do the hard one, you can do the easy one. You have a bonus, right? Just like ChatGPT, if you do not like your prompt, you can tweak your prompt a little bit. Can I make the sentence more polite? Can I make this sound more native, right? So if you want to ask if I don't like my galaxy, what is the closest one that will satisfy, like they will make like this galaxy, like outside the posterior. And this is the power that if you can do a generative models, you solve everything. It's what you want. It's a joint distribution that you care. It's not the conditional distribution that you care. The last thing is really about human, right? So you have your simulation. We talk about people arguing like the simulation are not science because they know more than we do. Can we gradually know what is being done in the simulation? And this can do that, right? So the problem with simulation is that if I want to study, say, what form the Milky Way, I can never find 2 galaxies that are exactly the same. So no matter what you study, you're always integrating over X and therefore smearing out Y's. Just like you cannot find 2 stack overflow questions that is exactly the same, right? But now if you have learned the distribution, then you can start to really sample on a single prompt and give you all the responses that satisfy the prompt. And this is very, very powerful. To give you a simple example, right? So let's say I want to know, how do I change the progenitor system so that I can form the same galaxy like the Milky Way? If you look at the closest TNG 300 sample, you see some correlation, but it's very weak because you are limited by the sampling noise. If I take the whole TNG 300, it's even worse because most of them do not look like the Milky Way. You wash out the correlation. But just like what Joe showed for spectra, if you can first infer the distribution, now you can condition on a single point, then you can start to see a stronger correlation. Just like, how do you learn languages? It's very hard to learn from Stack Overflow, but if you keep querying like GPT, you can start to build intuition based on the knowledge is already there. And this is why it's very exciting. Machine learning is not aiming to make simulation more difficult. It's also not only aiming to just do the inferences, but rather how you can slice the simulation in an intuitive way so that you can build intuition on that. I think that this is a point that I've been pondering a lot in the last year or so, and hopefully have convinced you that these are the signs. You can summarize the distribution. It's just a mind chatter. I will be happy to take any question and criticism and discussion about life. To stop here.
All right. Thank you, Jansen, for that great talk. Do we have any questions? Yeah, Paco.
So amazing talk and really, really beautiful work. This might be aware, but did you make all these movies yourself? Or?
Half of that. So sometimes I do pay people to make it, but these are all original. But I believe that in a year I do not even need to pay people. I can just find a way to generate. Yes.
Beautiful. Yeah.
Really enjoyed this talk. Could you say more? I think I missed it, or the part about which aspects of the Milky Way you were using?
Yeah.
Can you just?
Yeah. So this is a proof of concept. So here we are just taking things that in TNG 300 that we believe more or less can be measured by the IFU.
I see. Yeah. Okay. Okay. Got it. Thank you.
Yeah.
Yeah, sorry. So it's kind of a related question, I think. So my name is Toby Brown, and I always forget to say it. Thank you. So yeah, I'm thinking about observations and how you can use this and like basically to build up populations of like observations of progenitors from what you're working on. And then I was kind of thinking along the lines of what Risa was saying to then feed that back to the Milky Way properties we're actually interested in.
Right. So yeah, this is actually an interesting question. It's like a project that I hope to find a student to work on. Kind of like if you can do this, then you can start to ask, especially if you can do the joint distribution, you can really ask if I like eliminate some of the observation, how much variance do I get in terms of the graph, right? So essentially you want to ask is, what is the set of conditional variable do I need so that I can minimize the variances of all the output, right? So it's an interesting question. If you have good students, send to my way, I will work with him or her. Yes.
Yeah, I mean, I just had a very silly quote. Is that Ted Chiang, the author, in the Nature article?
Say that again? Oh, yeah. It's an article, so it's not like a proper science journal, but it's an interesting criticism about like a simulation, and that is in 2000, right? So this is not new. So people saying that like we are not knowing what we do, we already do not know what we do for a long time, and we are just approaching a limit where we start to be able to poke the beast, and this comes from like machine learning. So machine learning is not making things more opaque, but rather making things clearer, just like ChatGPT is making search better, not worse.
Louise Edwards, thank you so much for that beautiful and clear talk. I felt like I could understand you during the talk, and, you know. Anyways, can you help me understand a bit more about how these generative models are useful by giving me another example in astronomy of when we would use it? Like we made it really clear about how, merging.
Yeah, people have mentioned that a little bit already. The other example that people use a lot, this is all in the SBI like regime. Again, SBI is also a suit keyword like in astro machine learning. So too many things. Where are we? No. Okay. Yeah. So the whole thing about SBI is that you can make the inferences as you want, but also depend on if you are emulating the posterior or emulating the likelihood. In this particular work from Euros and also like Sultan work on that is emulating the images, and that is actually quite powerful. So so all these are inferences. It's really just saying that in many cases, if you can summarize everything can be a phenomenology. You do not need to go to the summary like statistic, like anything, right? Point clouds, like anything that you can imagine. A chair, like whatever, the alignment of people, they are all an observation. Yeah.
So Peter Baruzzi, this is a super nice talk. And I'm just wondering how this approach scales once we get more and more and more information, and therefore sort of more and more dimensions to our inputs. So just as an extreme example, let's say I wanted to run a constrained simulation of the Milky Way in the local group, and I would just put in all the observations of all the stars that I know into a generative model, and then I would get that back instead of having to sort of search for the best solution. And so at what point does that become unfeasible because the current technologies just don't accept that many dimensions as input?
Yeah, it depends on the symmetry, right? So the problem is that there's a debate about how many simulations that you can run like feasibly and how well you can describe the distribution. It's like, do you have the mean to first like project that into a lower dimensional like manifold? Of course, if you take all the stars, it would be really hard if you do not really tell how to compress the manifold. So, a point cloud of 100 billion stars, theoretically like possible if you are some alien like civilization, the whole planet is made of like GPU, then you might be able to make things happen. But it really comes down to mathematics and how you compress the dimension first. Yeah.
This is Matt Ho. I have a question on the other side of this,
Right.
which is you mentioned that you plan to extend it to the whole merger tree
Right.
at some point,
Right.
which I assume means the dimensionality of your graph just like explodes.
Yeah.
What is your limit here, and have you tested that?
No. So that's sort of like interesting thing that we want to do. Again, it's limited by teaching and no students. So yeah.
Okay, cool.
So maybe I didn't understand or you didn't say. So right now the graphs that you are generating, they have different number of nodes, then the edges can also be different, or is always...
Oh, so this is completely like varying. So here, exactly because of the technical slide, so I have to need to show you the matrix graph again. No. So this is exactly why this work is quite technically like appealing. Just go back to this part again, right? So the neural ODE, classically you have a fixed like MLP to do the integrand. But here we use the graph network, meaning that I can process 10 nodes or 20 nodes with the same graph network. So this is why you can do the reverse process. So the reverse process is that if I want to generate like 20 nodes, I will draw from a 20-dimensional like Gaussian and do the reverse process. If I want to generate 10 nodes, I will like draw 10 from a 10-dimensional like Gaussian and do the reverse process. But it's the same network.
But for the number of edges, for instance, what do you do?
The edges, here is the H. So here is a fully like connected graph, which is why if you do a tree, it might be easier because you kind of know the edges. But here is the progenitor. It's hard because you still have the lateral dimension, even the temporal dimension, you know how to connect them. The lateral, the simplest thing is a fully like connected graph, which is n squared. So that's quite.
There might be some application where maybe you don't want a fully connected graph, but yeah.
Yeah, so there's like latent edges. There are lots of things to be explored. So like graph and point cloud is a largely like unsolved question. So it's a very exciting field, even from the machine learning point of view.
Any other questions? All right, then again, I have a quick one. This is super, super cool. So when we do generative models for, like for images or for text,
right.
One of the ways that we tend to evaluate that as humans is just by, we're really good at looking at images and being like, that's a bad image or that's a good image.
Right.
How do you evaluate whether or not you made like the correct progenitor graph given an input?
Yeah, so this is even easier, right? If you based on the simulation, you are just maximizing the likelihood, meaning that I want to cover all the possible graph that has been like generated in the simulation. It does not solve the syntactic gap. You are just saying that given all the things that I have like generated, I try to find a canvas that will describe all the graph that has been like generated. I'm not sure to answer your question. So text is hard because there is no ground truth, and this is why they do a ranking. Sure. But for here, we do have ground truth from the simulation. Does not really means that you know the syntactic gap, but the generative model is also a way to do the domain adaptation. So that's all tied together. Yeah.
Sure. All right, let's thank Yuan again. It's a great talk.